All right. Hello, everyone. Welcome to lesson 21 of Calculus 1. So as a reminder, in this set of lessons, we're going through different applications of the derivative. And for the next few lessons, I would say lesson 21 through 24, what we're going to be doing is we're going to be analyzing the behavior of functions using the derivative. So as we'll see, we'll be able to find out if functions are increasing or decreasing, what their graphs look like, what their maxima and minima are going to be. We're going to be able to find out a lot about functions from these next few lessons here. So today we're going to introduce some important theorems to tell us some facts about functions that end up being useful in some instances. The first theorem that we're going to start with is called Rolle's theorem. And Rolle's theorem says that if the following three conditions are true, so if we have a function that is continuous on the closed interval AB, including the endpoints, and if we have that same function being differentiable, meaning it has a derivative on the open interval containing this endpoint. So I suppose it could fail to be differentiable at A or B. And finally, that the value the function takes at the first endpoint is the same as the value it takes at the second endpoint. So if we have all three of these conditions met, then there is a x value in the interval AB where f prime of c is going to be 0. So if we meet those three conditions, then we know there's going to be some point where f prime is going to be 0, or in other words, we're going to have a tangent line with no slope, or a flat tangent line. So here's a picture to illustrate this. So let's say this is A, and then B needs to be at the same height here. And then let's say we have our function that's continuous and differentiable, and it's connecting these two. So what this theorem is saying is that there is at least one point, possibly more than one, where our derivative should be 0. And in fact, actually in this one, we can see that there's going to be more than one possible c value, because it seems like the derivative is 0 here. We have a flat tangent line. And also down here, it seems like we have a flat tangent line as well. But what Rolle's theorem says is that there's going to be at least one point like that. There can't be no points like that. All right. One thing I want to say about Rolle's theorem, and this is going to be true of some of the theorems we're going to learn about in this class, Rolle's theorem doesn't tell us how to find this special x value c. So all Rolle's theorem says is that this c value is going to exist. It doesn't really tell us how to find it. Now, if we know how to take the derivative of our function, we could set it equal to 0, and if it's algebraically amenable enough, we can solve for what c has to be, but that's not going to be the case for all functions. All Rolle's theorem does is tell us that a c will exist here. All right, now what is the use of this theorem? So what if the derivative is 0 somewhere? Well, let's take a look at an example. Let's say that we have the function 5x minus 10 plus e to the x. And what we want to do is we want to show that f of x has only one real root. So remember, a root of a function is an x value that makes this be equal to 0. Now you might be like, okay, well, why don't we just set this equal to 0 and see where that's going to happen? Unfortunately, we can't algebraically solve this equation here. That's not going to work out, because anything that will undo this exponential right here will turn this part into a natural log. So I don't think there's going to be an algebraic way of solving this equation. Okay, so this type of problem has two steps. So step 1, find at least one root. Okay, so how are we supposed to find out if there's one root? Well, you may remember back many lessons ago, we learned about something called the intermediate value theorem. So this says that as long as our function is continuous, and f of x is continuous, because exponentials and polynomials are continuous, then if it's below 0 in one place and above 0 in another, it must pass through 0 somewhere in between. So let's take a look at f of 0. So f of 0 will be 0 minus 10 plus e to the 0, which is 1. So f of 0 is negative 9. So we know that this function is negative somewhere. And then on the other hand, if we look at f of 2, this is going to be 10 minus 10 is 0 plus e squared. So this will be e squared right here. And we know that e squared is greater than 0. So this is less than 0. This is greater than 0. So the intermediate value theorem, the IVT, says that there is a c in the interval 0 to 2 where f of c is equal to 0. Because the graph is continuous and it's below 0 at one point, above 0 at another, so it must pass through 0 at least once in between these. Okay, so we now know that there is at least one root. So it's going to be wherever this c is. And note, we didn't find out what c that is. We can maybe numerically approximate that c, but again, we can't just set this equal to 0 and solve it. So we know there's at least one place, and it's in between 0 and 2, where we're going to have a root. Now, the problem specifically says that we want to show that f of x has only one real root. So for all we know with the IVT, maybe there's more than one place that we cross 0. Like maybe, for example, our function does something like this, where it crosses 0 multiple times. So we want to show that that's not going to happen here. So what we're going to do is we're going to use Rolle's theorem for this. So step 2, show that there is no more than one real root. All right, one common technique in mathematics, if you're trying to show or prove something, is called a proof by contradiction. What you do is you suppose the opposite of what you want to prove, and you show that that leads to some kind of absurdity or a contradiction. So what we're going to do in this case is we're going to suppose there are at least 2 roots. And let's call them C1 and C2. So we're going to see what happens if there's at least 2 roots. So we have C1, C2, maybe we could even have more like C3, C4, but it's not really necessary to write those down. I guess we could just put dot, dot, dot here for however many roots there are. Then we know, and then let's further suppose that C1 is less than C2. So this is going to be the root that's smaller than this one. So this x value is going to come first before this. Remember, these are all x values that we plug into our function to make it 0. All right, so let's take a look at what we know. We know that f is continuous on the interval C1, C2, because f is continuous everywhere. This function is continuous everywhere. We know that f is differentiable on the open interval here, because again, we could take the derivative of this and that's going to exist everywhere. And then finally, we know that f of C1 equals f of C2. And why do we know that? Well, because they're both roots, so they both make the function be 0. So notice that with these 3 facts, we satisfied the prerequisites for using Rolle's theorem. So what does this tell us? So this tells us that there is an x in the interval C1, C2, where f prime of this x value is going to be 0. Okay, well, again, that kind of seems like a harmless statement, like, oh yeah, okay, so the derivative's going to be 0 in there, so what? Well, let's take a look at the derivative, because we know the formula for this. So we should be able to find the derivative. So f prime of x, let's see, we get 5 from this, 0 from this, and then e to the x. All right, now this is where something weird starts to happen. We know that 5 is, of course, a positive number. We know that exponential functions are always positive. So that means that the whole thing has always got to be greater than 0, no matter what our x value is. But on the other hand, according to Rolle's theorem, there should be a place where our derivative is 0. So we see that these two facts can't both be true. So all of our reasoning was correct. The only thing that could be wrong is our assumption here, that we have two roots. So this is a contradiction. So this means that f of x has only one real root. All right, so there we go. So this is Rolle's theorem. It may seem kind of innocent here. Oh, we're just seeing that f prime has got to be 0 somewhere. But that can actually tell you a lot about our function. That's going to be the theme of these few lessons that are coming up. We could use derivatives to tell us facts about our function that we might not have been able to use with algebra. Like, for example, we can't just algebraically solve this equation for 0 and see there's only one solution. We can't get any solutions for real algebra for this. All right. So I want to talk about another theorem. And it turns out this theorem is actually a generalization of Rolle's theorem. So it's kind of like Rolle's theorem, but it can be more versatile. And this is called the mean value theorem. And this is very commonly abbreviated MVT, and I'm going to call it that for the rest of this lesson. All right, so this theorem is very similar to Rolle's theorem at first. So if f of x is continuous on the closed interval a to b, and I keep wanting to write f prime, and f of x is differentiable on the open interval a, b, so this is so far identical to Rolle's theorem. But one thing that's going to be different is we're not going to have that third requirement. So that's why this is more general, because it works even if f of a is not f of b. Okay, well, then what's the conclusion going to be? Then there is an x value, which we're going to call c, in the interval a, b, such that f prime of c is f of b minus f of a over b minus a. So this is the conclusion of the mean value theorem. Okay, so this isn't as nice as just having something be 0, but we do get some kind of equation for what f prime is going to be. Now, what's the significance of this quantity right here, f of b minus f of a over b minus a? What this is this is the slope of the line connecting a f of a and b f of b. So this is the slope of the line connecting the 2 points on the graph that we're looking at in the interval between here. So let's draw a picture again. So let's say maybe my a is back here, and then let's say b is here. And maybe it's a different value than a this time, and it could be smaller as well. The same thing will work. So here is the line connecting these, right? So this is the line I was talking about here. And this is going to be the slope of this line, because it's the rise, the difference in the function value, over the run, which is b minus a. Now let's say the function looks something like this. So what this theorem is saying is that there's got to be a point where the slope of our tangent line is the same as the slope of the line connecting these 2 points. And we could see that that happens right about here. So if we look at the tangent line right there, you see that it has the same slope, where it's parallel to the line connecting these. And just like Rolle's theorem, there could be more than one place where this happens as well. All the mean value theorem says is there has to be at least one place where this happens. So one way to kind of imagine the mean value theorem is you can imagine that it's Rolle's theorem tipped on its side here. Actually, if we rotate this like this, we see that these are level with each other, and then we have these lines parallel to 0, y equals 0. So that means that these we'll have f prime being 0. So essentially, the mean value theorem is Rolle's theorem where we're allowed to rotate it. And you can see that Rolle's theorem is actually just a special case of the mean value theorem, because if we have that third assumption here, f of b equals f of a, then f prime of c will be f of b minus f of a over b minus a, but since these are the same number, that will be 0. So you can imagine that Rolle's theorem is kind of a special case of the mean value theorem here. And again, I want to offer this note here. The mean value theorem doesn't tell us how to find c. So this is what's called in mathematics an existence theorem. It tells you that a particular number or object exists, but it doesn't give you a way of finding it. So there may be actually no way of computing specifically what c is, but the mean value theorem guarantees that it's there. And sometimes that's enough for some purposes. And as a matter of fact, many of the most important theorems in calculus come from the mean value theorem. And this kind of seems strange, like, oh, what's the significance of there being a tangent line parallel to the line connecting these? We'll actually see this in quite a few lessons from now, but we're going to use the mean value theorem to prove something very important. We're going to see that something very important is true because of this. All right, so let's try to do a problem using the mean value theorem. All right, let's say that if f of 1 is equal to 2 and f prime of x is greater than or equal to 5 for all x, what we want to do is we want to find the smallest possible value of f of 4. So this is our objective here. We know what the function is at 1, it's going to be 2, and we want to find out what the smallest possible value is at 4 if we know that f prime is always going to be greater than or equal to 5 here. All right, well, assuming that we have a derivative that's defined for all x, we know that f is continuous on the interval from 1 to 4. Because that seems to be the two x values we're interested in, so we might as well consider that interval. And we also know that f is differentiable on 1 to 4, because they didn't really say anything about a domain here. In fact, they give us this inequality for all x, so we can assume that f prime is going to exist for all those x. So we've satisfied the two conditions for the mean value theorem. So this allows us to conclude that there is a c in the interval 1 to 4 where, and then let's write the equation, f prime of c is f of 4 minus f of 1 over 4 minus 1. All right, now let's see here. We know what f of 1 is, that's going to be 2, and we can obviously do 4 minus 1. So this is really f of 4 minus 2 over 3. Now what I'm going to do is I'm going to multiply the 3 over here and then add 2. So this gives us that 3 times f prime of c plus 2 has to be what f of 4 is. Okay, well, that's all well and good, but we don't know what the c value is, and we don't have a formula for our function, so we can't take the derivative and directly plug it in here. So how are we supposed to know what f of 4 is? Well, one fact that we do know is that we know that the derivative anywhere for all x is going to be greater than or equal to 5. So at a minimum, this has to be 5. So this is going to be greater than or equal to 3 times 5 plus 2. And this is the smallest it can be. Remember, f prime could potentially be bigger than 5. This is just the smallest scenario. But that's actually what we're looking for. We're looking for the smallest possible. So it makes sense that we're going down in size. So we have 3 times 5 plus 2. So this tells us that f of 4 needs to be greater than or equal to 17. Even in the case where f prime is as small as possible, where it's always 5, we're still going to have to get to at least 17 for f of 4. So 17 is the smallest value that f of 4 could be. All right. So let's see here. Here's another example. Suppose a police officer tracks a car and the car travels 20 miles in 15 minutes. Was the driver speeding? All right, so I know that the other examples have been very abstract, but this one is a bit more concrete. So let's say that we have this car and we know that it goes at least 20 miles an hour. Oh, I guess I didn't specify a speed limit. Let's do the Florida's highest speed limit. Was the driver speeding if the speed limit is 70 miles per hour? All right, well, actually the mean value theorem, believe it or not, can tell us whether or not this driver is speeding here. So what we're going to do is we're going to have our initial time is 0, and then our final time, t1, will be 0.25 hours, because that's how long 15 minutes is. So by the intermediate value theorem, assuming that the driver's position function is continuous and differentiable, we know that there is a time, let's call it t, where f prime of t, where let's define f of t, is the position of the car. So we know that f prime of t needs to be f of 0.25 minus f of 0 over 0.25 minus 0. Now let's mark the position where the person starts as 0. So this will be f of 0.25 over 0.25. Now they say they travel 20 miles in 15 minutes. So we'll say that f of 0 is 0 and f of 0.25 is 20. All right, so this is going to end up being 20 divided by 0.25 or a quarter, which is 80. So what this is saying is that there is a time where f prime, and since this is position, this must be the velocity of the car, is equal to 80. So we know that at some point, maybe not the whole time, but at least at some point, the velocity of the car is equal to 80 miles per hour. So if we have this information, then we can conclude that the car was speeding by using the mean value theorem here. And you can actually see why the mean value theorem has its name. Mean means average. And essentially what the mean value theorem says is that the instantaneous rate of change will at some point equal the average rate of change. So for those of you who took physics in high school, you could determine that the average velocity is 80 miles per hour. It's the total distance over the total time. And we see that because of the mean value theorem, the instantaneous velocity will end up equaling the average velocity somewhere along the way. So that's what the mean value theorem is telling us here in layman's terms. So in addition to being of theoretical importance and being able to just tell us about abstract functions like this, we could also see that it applies in real life as well. All right, so I'm going to state a few more theorems that are going to be of some use, and these can be proved using the mean value theorem and Rolle's theorem. So here's a theorem. If f prime of x equals 0 in an interval a, b, then f is constant. in AB. So this is saying that the only functions that are constantly having a derivative of 0 must be constant functions. As a corollary or a related theorem, if two functions have the same derivative in some interval, then f of x is g of x, but maybe off by some constant in that same interval. So if two functions have the same derivative, they can at most differ by a constant. So here's a picture showing this. Let's say that f and g have the same derivative. Then if this is going to be f of x, let's say that's what f of x is, then g of x needs to look something like this right here. So what this is saying is that if two functions have the same derivative, then the shape of their graph is the same. The only difference could possibly be that one is shifted up or down here. So there might be a gap of the c right here between these two functions. And I'm not going to go into the proofs of this. I'll save that for advanced calc, but both of these can be proved using the mean value theorem here. All right, so what I want to do a few more examples, practice problems with the mean value theorem here. So here's an interesting example. One fact that we use very often is that sine squared plus cosine squared is equal to 1. So what we want to do is we want to prove that this is true. All right, so we're going to use this fact up here. If f prime is constantly 0 in an interval, then f is constant in that same interval. So let's say that f of x is the function sine squared plus cosine squared. Then we can use our derivative rules to do f prime of x. So we bring down 2 here, and then we have sine of x, and then the derivative of sine is cosine. Here we do the same thing. We have 2 cosine of x, but then the derivative of cosine is negative sine. And you can pretty clearly see that these are going to be the negatives of one another, meaning that our derivative is going to be 0. And a lot of times when someone wants to say that it's 0 all the time, you could put 3 equal signs, meaning that it's going to just be the 0 function. We're not setting it equal to 0. So by the theorem that we talked about up here, if your f prime is going to be 0 in the whole interval, then f must be constant in the whole interval. And because f of 0 is equal to 1, that implies that f of x is 1, because f must be constant. So if it's 1 in one place, then it's got to be 1 everywhere. All right, let's see here. Here's another example. You may find a lot of this on your homework here. Find C for the mean value theorem if f of x is x squared plus x plus 1, and we have the interval 0, 1. All right, so let's see what the mean value theorem says about this. First of all, we need to make sure that the mean value theorem applies. F is continuous because it's a polynomial, and f is also differentiable because it's a polynomial. So we know we could use the mean value theorem here. So now we know that f prime of some c value will be f of 1 minus 0 over 1 minus 0. So f of 1 is 1 plus 1 plus 1 is 3. And I plug in 0. 0 plus 0 plus 1 is 1. And then we have 1 minus 0 down there. So what the mean value theorem tells us about this situation is that somewhere in the interval from 0 to 1, this function must have a derivative equal to 2 in here. Now, unlike the examples we looked at earlier, this one we actually can find the specific c value. So f prime of x, using our derivative rules, we know is 2x plus 1. And what we're going to do is we're going to set this equal to 2. Now, if the mean value theorem is correct, we should be able to solve for an x that's somewhere in between these numbers. So if I subtract 1 and divide by 2, indeed I end up getting x equals 1/2, which is actually right in between those two right there. So we know that f prime of 1/2 gives us the promised value of 2 here. All right. So I want to state a few more results here, and then I want to talk about a very, probably one of the more important theorems we're going to be learning here. So in the beginning, I use this word monotonicity as the name for our lesson here. What is monotonicity? It means doing the same thing, like continuously. So for example, if someone speaks in a monotone, they speak in the same pitch continuously. In mathematics, monotonicity refers to a function always increasing or always decreasing. So we end up having these two facts here, and I may have accidentally used these in previous lessons, but here I'm going to explicitly state them. If we have a derivative being positive on an interval a, b, then f is increasing on that same interval. So having a positive derivative corresponds to increasing. And then, as you might imagine, if we have a negative derivative on some interval, then f is decreasing on that same interval here. And just like some of the other theorems we used earlier, we could use the mean value theorem to prove these here. All right, so these are going to be some facts that we're going to use quite a bit in a future lesson here. We want to find where our functions are increasing or decreasing. All right, and I have one final thing to talk about. There's a lot going on in this lesson here. I want to talk about something called the first derivative test. Now, this isn't called the first derivative test because it's the first in a series of derivative tests. It's more combining these two terms together. We're going to use the first derivative to tell us something about our function here. All right, so what does the first derivative test say? If f prime of x goes from positive to negative over a critical point, then the critical point is a local maximum. So remember what a critical point is. A critical point, as a reminder, is a place where f prime of x is 0 or undefined. And we also have the condition that x is in the domain of our function. All right, so that's what a critical point is. I believe we talked about those in the last lesson. So what this is saying is that if we go from positive to negative, or in light of this, if we go from increasing to decreasing over a critical point, then we're going to have a local maximum there. And then, as you can imagine, if we have things the other way, over a, I'm going to call it crit point, then the critical point is a local minimum. All right, so if we go from decreasing to increasing, in other words, we're going to have a local minimum. And the third scenario is if f prime of x doesn't change sign. Like maybe it's positive and then it stops for a moment at 0 and then it continues being positive, or same with negative. It's neither extreme. All right, so we don't have a local max or min if it does something like that. All right, so here is a picture explaining what's going on with this. So let's say we have a function that looks like this. It starts like this, and it's flat down here, and then it levels off for a moment here, and then it sort of spikes there, and goes down like this. All right, so we can see here at this point, this is a critical point because we're going to have a flat tangent line. Now you see that we're decreasing over this interval, meaning f prime is less than 0. We stop here, and then we have a short interval where f prime is greater than 0 from here to the origin. So since we're decreasing and then we're increasing, then we're going to have a local minimum. As you can see by the picture, this is going to be smaller than any of the other points nearby. This is an example of case 3. We're going from increasing, and then in the next leg of the function, we're still increasing. So we don't change sign over this critical point, even though we are flat for a moment. So it's not going to be a minimum or a maximum. And then finally, we have a critical point right here. We have f prime greater than 0 before, and then since we're decreasing, we have f prime being less than 0 afterwards. So this right here is going to be a local max. And notice that this wouldn't be a flat tangent line. This would be where our derivative doesn't exist. But that still counts as a critical point. So that illustrates cases 1, 3, and 2, respectively here. So that's what's going on pictorially for this theorem. All right, I know this video is a little bit long, but I just want to do one example where we do, we use the first derivative test and we learn about a function. So what we're going to do is we're going to find the local extrema, and we learned how to find absolute maxes or mins in the previous video. So if you want, you can do a practice with that. Find the local extrema and intervals where it's increasing or decreasing for the function f of x is 2x cubed minus 9x squared plus 12x plus 6. All right, let's take a look at this. So the first derivative test naturally is going to use the first derivative here. So we're going to have f prime of x. That's going to be 6x squared minus 18x plus 12. And notice that 6 goes into all of these. So we can end up making it look like this. And actually, we can factor this as well, so we can make our derivative look even nicer. All right, so there we go. So we have our derivative here. All right, now let's try to find our critical points, because critical points are critical to the first derivative test. Critical points occur when our derivative is undefined or 0. Now, this is a polynomial, so it won't be undefined anywhere, but it certainly will be 0. It's going to be 0 at x equals 1 and x equals 2 right here. So these are going to be our 2 critical points. Now, to use the first derivative test, we typically draw a number line here. So we're going to draw a number line. We're going to put f prime on there. And then what we do is we put down on our number line any critical points. Now, a lot of people like to use 0 and put extra numbers into their number line to flesh it out. I recommend against doing that. You'll see why in a second. It's going to make things a lot more cluttered if you do that. All right, so we put our critical points down. Then what we're going to do is we're going to test a number before the first one, in between the 2 right here, and then after the last one. And if we had maybe 3 critical points, we would test in between all of them. So however many critical points you have, you're going to have to test one more than that numbers in our derivative. All right, let's plug in a number that's before 1 into our derivative and see what sign it is. We only care about the sign, not the specific value. So if I plug 0 in here, I get a negative. If I plug 0 in here, I get a negative. So negative times negative is positive, and then we have a positive. So f prime is going to be positive before 1. All right, now let's plug a number into here that's in between 1 and 2, like maybe 3 halves. 3 halves minus 1 is positive, but 3 halves minus 2 is negative. So we'd have negative, negative, positive. So we're going to get a negative there. And then finally, if we plug in something bigger than 2, like maybe 3, we're going to have positive, positive, positive. All right, so this is what our f prime is doing here. So we know that it's going to be increasing in this interval from negative infinity to 1, so before 1 up to 1, and it's going to be increasing in the interval 2 to positive infinity, but for a short while in the middle here, it's going to be decreasing from 1 to 2. So we know the intervals where it's increasing or decreasing. And by the way, one common way to combine disjoint intervals like this is we would write negative infinity to 1, and then we put this U or union symbol here, and then we have 2 to infinity. All right, so we've done the second part of this. We've done the intervals where it's increasing or decreasing. And then what we're going to do is we're going to label local maxes and mins. So here we're increasing and then we're decreasing. So by the first derivative test, since we're going up and then down, we're going to have a local max. So x equals 1 is a local maximum. And then we have the reverse situation happening here. We're decreasing and then we're increasing. So it's going to be something like this. So x equals 2 must be a local minimum right here. So we also found our local extrema. Now remember, these are local extrema. This function actually gets larger without end. As x goes to infinity, this will go off to infinity. But as x goes to negative infinity, this will also go down without end. So this function has no absolute mins or maxes, but it does have some local mins or maxes. Now, it would have absolute if we limited, say, where it's defined, but the problem said nothing about that. All right, that's it for today's lesson. So we learned a lot about functions using the first derivative. Next class, we'll learn more about, or we'll learn about finding out about functions using the second derivative. So I'll see you guys then.